going back to our course, there is a thing that is pretty, so this is called index theory. It's pretty because, anything topological, anything that just depends on kind of shape of things and doesn't require a million digits of precision, it appeals that it's very pretty. Now, my problem with index theory and today's application is that, as far as I can tell, you correct me if I'm wrong, as far as I can tell, it only works in 2 dimensions. And if you do any research for a hedge fund or for National Science Foundation or for an engineering company, you will almost never live in a plane. It's always going to be more dimensions. So I'll just give you a little sketch of what it means. Very often what happens in 2 dimensions, again, it's much harder in higher dimensions, is that you are given some complicated equations, not these equations I'm constantly feeding you from Strogat, something that has lots of variables, parameters. When you look at this equation, you have no idea what's going on. But you are told that you should first find equilibrium fixed points, to get some footing in this state space. There are things that don't move, so you can hang on to them. And then you explore neighborhoods using the stability and the eigenvector stability, stable, unstable manifold. That's always the strategy in this problem. Now, how do you find them? So one idea is that you can kind of blindly start exploring, and maybe you have a fixed point. It happens in attractive fixed point. You have stuff that goes in. And unfortunately, this is kind of intuition from the plane. So, and maybe it's not so trivial, it's just straight lines falling. An idea of index theory is to say, could I just wander and come back and as part of our exploration and see whether I have lassoed or fished in? So could I just go any place and say, aha, I have caught a fixed point? So then what you could do is, as you move over any loop, so you move, let's say, counterclockwise on a loop, you go this way. And at every point, you have your equations. So you can record direction of local velocity field of your flow. You can just look at the orientation of the field as you go around. So here is time 1, 2, 3, 4, 5, 6, and 7 equals 0, my starting time. You do it at few points. But hopefully, nothing dramatic happens in between. Then you look just at the vector field. So you're sitting here, you're one-dimensional little ant going around here. But you have a dial in front of it, and the dial is the angle of the field. So it's pointing this way. So that's a negative. And we won't even pay much attention to its magnitude, just to orientation. So at 0, I'm here. At 1, I'm here, pointing this way. At 2, I'm pointing this way. At 3, I'm pointing this way. At 4, I'm pointing this way. At 5, I'm pointing this way. And at 6, I'm pointing this way. And then at 7, I'm back. So now what's happened in this period, your little dial was moving, and maybe it was going a little bit back and it was going forward, and eventually has to return to original position. And then you say, well, the angle is that, the angle after one period, after return, or my arbitrary loop, the angle is some number. He says this is the contour C, and you have an index C, so it's some integer, because by the time you come back, you have to be a multiple of 2 pi. And now this integer can be various things. So in the same situation here, what I could have done, I could have run around. It's the same field, but my contour is different. This guy going there, everything as before. I'm drawing the same picture, not very well. But what happens with this other contour, in this case, what happens is the field goes this way, as I do this, and then it just goes back. And I find that this one has multiple 0. So it turns out this contour has not fished in a fixed point, attractive fixed point. Well, this one will have contour. So this one says there is at least one fixed point that's sucking stuff in. Then you can start playing with this, and this is very much like Gauss' theorem in electromagnetism. And if you have had any complex analysis, it's very much like Cauchy theorem in complex plane. If there are several points within the loop, the angles might add up, larger index, so they can cancel, various things can happen. Or you can distinguish what kind of point you have. Suppose you have a saddle point. So you have a fixed point, which has a stable manifold and unstable manifold. Everybody was, falling in, believing this is stable, discovering it's unstable. So you get what's called hyperbolic type trajectories. And now when I try to lasso this thing in, so I take my contour C, and I, walk around in the counterclockwise way, and I write this dial, and I number all these intersections. Something will happen with this dial, and if you follow it, and I'll leave it to you to see what the index is, but the idea is that every one of these things has different indices. Some of them are +1, some of them are -1. If you have several fixed points, they can add up, subtract, etc. And this gives you some topological idea, not only that fixed point exists, but what kind of fixed point exists. So fixed points of different kinds get different indices, these integers. And that's very topological and very robust. And sometimes you really use this if you're fishing in a plane for fixed points. So you have no idea. For you to try different curves, once you get a non-trivial index, you start tightening them. And then you have a very good guess to use other methods how to find where there is a fixed point in the state. So this is all I'll do about index theory here, because I never use it in my work. So I feel, bad about emphasizing it too much. And the reason why I don't use it is because this doesn't generalize robustly to higher dimensions. What happens in higher dimensions is that, you can wiggle around and you don't get very clear answers. It's harder to define, binding numbers of this vector field. It's still true that as you move in higher dimension, at every point there is local velocity field, it's pointing some way. It's still true that when you come back, it has to either point in same direction, and it turns out sometimes it can point opposite directions. So it has a minus sign once you make one total cycle. But there is no good way of defining winding in higher dimensions because you can deform these curves in various ways and not getting much information. It's not a very robust concept. Next thing that we have to discuss is this is a beginning of bag of tricks to finding equilibria. That's the first thing to do. But sometimes you can show that there is no equilibrium either in your problem or in the region of your problem that you care about when you're exploring it. In that case, the first topologically invariant object that Flo has, he calls limit cycle. This idea of limit cycle intuitively says that as I'm in the plane and I wander around in the plane, what can happen in a plane, especially if I don't have any equilibria. I can start someplace, and in a plane I can just run off. And if there are no fixed points, I can just come from infinity and go to infinity. So that's one possibility. But other possibility is that I can start someplace and after period t, so I start at x times 0, 2 dimensional. I go, and there is a period, a given time t, where I exactly come back. So that's one possibility. Then you say, well, what happens if I miss? So what happens? I'm not very good in guessing what comes back, and when I'm in the vicinity of initial point, I'm a bit away. So what happens when xt is not x0? I'm in the plane, I have a trajectory. If I miss, then I have to go someplace. I cannot cross inside, so I have to go outside. So I either end up going to infinity or I end up falling into some fixed point, or I end up in limit cycle. So there is no way in 2 dimensions to avoid limit cycles. Either you have nothing that's invariant, or you have equilibria, which you already know we have to find. And if you don't have equilibria, the next best thing is we can have a set of points which in time just gets permuted where the points are, but the entire set is invariant. And those things, if they have a finite period, they're called periodic orbits. Acting as we did before, different fixed points. You go in unstable direction from one and stable into other one. They're called heteroclinic connections. Those are infinite trajectories, but pinned at the 2 ends. Or you can come back to yourself. That's called homoclinic. Or you have periodic orbits. So repertoire of things you can do in a plane is very small. And sometimes they really limit cycles in the following sense. You find out that once you're close to it, it keeps sucking you in, and you get closer and closer. And our intuition we have from fixed points is that, if fixed points have stability, which is hyperbolic, a finite eigenvalues for fixed point. for cycles, they will mean that you're getting exponentially close. So your computer after a while cannot tell. And if you start someplace inside, same thing happens. You can only spiral. And now you're not allowed to spiral to infinity because you're in a plane and there is a barrier. It's this set. So the only thing you can do, you can end up on this set. And that's what I call limit cycle. So this is very special kinds of periodic orbit, which is the next best thing to attractive periodic equilibrium, point that you fall in. Here what happens, you don't fall into the point, you fall into an invariant set, which is this curve. And what happens on this curve is at any point that you start with, any point whatsoever, so point at time t, you march on it, and after the period, you come back. So it's a periodic orbit which is attractive. In the plane, there is another kind of periodic orbit which has a property that if I start close to it, I wander away. So, I start very, very close, someplace here. And if I'm outside, there'll be kind of deformed spiral. They'll eventually go someplace else. And if I'm on inside, I'll get repelled by this thing. But my freedom is very limited inside. So what can happen inside is I can either end up on a smaller limits, or maybe there'll be initial conditions which will end up on an attractive fixed point. So this kind of thing is a periodic orbit, but it's an unstable periodic orbit. Unstable periodic orbit is a limit cycle going backwards in time. So, I don't like to call it limit cycle because if you did a simulation on a computer forward in time, you would just be thrown away. You would never notice it unless you're very careful. Whereas with the limit cycle, you always fall in. So these are just generalizations of idea of attractive and repulsive fixed point in one dimension. And pretty soon we'll make this very explicit because we'll say, well, following this thing is a little bit tedious. So let me just put a line across. And what happens on that line is that you can mark, for every return, you can mark the points on this line. And you can actually compute the stability transfers to the orbit in this direction. And then this becomes a fixed point problem. So this method, which we'll do later at some length, is called Poincaré section. So in developing the theory of qualitative theory of differential systems, Poincaré realized that when you have an invariant set on which nothing really happens, points just run around it under time, you only care what happens to its neighbors, not along the set because they march to each other, but transversely by looking how the neighbors of your set away from your loop work. And what that does, it makes this problem just a fixed point problem, Poincaré section, and we know how to do fixed points. Now, this idea is good in all dimensions. And a surprising thing that will happen is that while sometimes there will be limit cycles, there are problems in which you start any place and you fall into periodic motion, which is robust. Perturbations don't do it. When you study chaos, when you study what happens to systems which are locally unstable, everything lives on unstable periodic orbits. There is infinity of them. The stable ones either don't exist or are very exceptional. And, that's kind of message that will go on further in life. And of course, then there are marginal cases. There is a border between the two, in which it turns out that as you go around, as far as linear stability is concerned, as far as measuring the distance linearly in transverse direction, in Poincaré section, you get a 0 eigenvalue. And then you have to do nonlinear analysis of kind that we have done. But basically, there are in-between cases you have to understand. But they are exceptional because they only have for one parameter values in the big parameter space. And we will ignore this for now. So let's look at a few simple examples. This is qualitative theory, but it's very easy to stick it on computer and do a number of it. There are lots of pretty examples, and this one I've used in my reason, like it. So simple. It's one that we have already done. We wrote it in Cartesian coordinates, x and y's, and it looked kind of complicated. There are cosine, sines, and God knows what. But when you look at cycles, things that are periodic, the first approximation that comes to mind is a circle. It's a simple cycle. So that tells you that very often these problems are profitably written in polar coordinates in terms of distance and angles rather than in the Cartesian ones that are presented to you in your lab. So the one we looked at is you have equation in polar coordinates where the radius looks like logistic equation. And the angular motion is just very simple. You move at constant velocity, which you set equal to 1 by rescaling this and that. And now, this is now a separable problem. There is a radial coordinate and nothing is happening in the angular coordinates except orientation is changing at uniform. So this one you know how to do. This problem has two fixed points. So there is, r equals 0. But then there is also r equals 1. So as far as r is concerned, I'll do it in Cartesian coordinates. It's easier for us to understand. But so this is x and y. And there is a fixed point here. And this is slope 1, so this is an unstable. So if theta equals 0, we're just on x line. And then there's another fixed point at 1, radius 1. That one is stable because slope is negative, and you know how to compute this. And this is now at theta equals 0. But our frame is rotating. So this traces as theta changes at uniform velocity. This traces out a unit circle, which after time 2 pi, you're exactly back. And it's defined to go counterclockwise, okay. And now, you know what happens to this guy. This is unstable. So if you start here, if you're not in rotating frame, you'll be exponentially moving out, but because your frame is moving, anybody who starts close to this will spiral out. And exponentially fast in radial coordinate approach the limit cycle. And anybody who starts outside the radial, when r is larger than 1, this dominates with negative sign. So you will be falling in. And voila, the simplest example of limit cycle, which is in rotating frame, it's trivial, it's just that. But if you have something in your frame, it'll be spiraling in and spiraling out. And you can also see there's a deep connection between fixed points of this and limit cycles. You also see the other thing about this kind of cycles. I decided there is a tradition there where you look at one of the fields. There's a y and x and y field here. So let's look at x of t as a function of time. People often plot such things. After a while, you don't want to plot them because time goes to infinity, so it's not an infinite piece of paper. But what happens is if you start any place, you will be approaching the cycle, and eventually you will just have a sine cosine kind of thing. And I didn't do it very well, but there'll be an envelope, so there'll be transient, and then after a while you'll be just caught oscillating in a usual way. So that's kind of trivial, but then there's infinitely many very interesting clocks, especially biological clocks, which we'll discuss today, or chemical clocks, which have not trivial, they're nonlinear problems. So limit cycles are not necessarily circles, almost never are, but they have a property, they have some geometrical shape and different velocities you move around. And the most famous of those came from the era that I still overlapped with. I've built electronic devices with tubes as a child, but you probably haven't seen many tubes in your life. So there is something called van der Pol oscillator. That one, historically was very important. I even have a book, an entire book about van der Pol, his life and the oscillator. And, it's an oscillator. So harmonic oscillator, you have a displacement, you look at the acceleration, it has to be balanced by the force. So if there were just harmonic oscillator, you had something like that. But in van der Pol case, there is a nonlinear term that appears there because tubes which were used to create radio waves and amplify them, etc., are nonlinear devices, and a good model is this equation with a friction term. Now it turns out this doesn't really work with like friction, because for friction we need a sign to be negative for energy to be decreasing, but this combination x squared minus 1, this nonlinear term, can change sign depending whether x is larger than 1 or smaller than 1. So this device actually describes phenomenologically how you drive electronic tube. You know, it's losing energy because you have to radiate stuff, but the energy can be put proportional to the current put into the device, roughly speaking. The main thing is that this term means that you can have positive or negative. And the positive one is okay. You know, positive one says, I'm losing energy. But negative says that I actually gain energy. So you pump in energy. And what this oscillator will do is attain some balance between pumping stuff in and pumping energy in and losing it. And that thing is, I will just copy the sketch of it. So if you're in a x and x dot plane, the limit cycle will turn out to be very distorted. And I'm drawing it very badly. So this limit cycle still has a property that after one period, which you have to compute in this particular case, I'm back. Every point on this limit cycle returns exactly after one period. But what happens in between is sometimes they speed up, sometimes they slow down. And so the motion within the cycle is very much unlike motion of a harmonic oscillator or a pendulum or something that's turning at constant speed. These two things are coupled, and it's not a separable problem. There is no constant speed. And that's very typical of biological clocks and things that, for example, you do in neuroscience when you have to reset. You can have periodic firing of a neuron, and what will happen is that when neuron is ready to fire, it'll suddenly discharge lots of electricity, which will mean that you're going very high on this line here. And then it'll get exhausted because it's discharged whatever electricity it had, and then you'll have to wait for a while until chemicals build it up. That's called resetting time. And that extreme version of oscillation is called burst oscillators. They go crazy and then they're very, very, nearly dead for quite a while until they again rebuild the strength and they go there. So this is a very interesting generalization of notion of oscillations. What happens is if you describe this in terms of Fourier components, different period oscillations, well, for motion of a circle, you only have sine and cosine. Here you have high multiples of these things, and it's non-trivial things to do. You will see high resonances in the spectrum. One thing that's useful in a plane, the next thing I will show you actually is true generally. Can one say that my system has no periodic orbit? Simple set of systems called gradient. It was damp pendulum. So there are lots of systems where you just lose energy because there is friction, and you end up dead. So there is no way to have a periodic motion. So one of class of such systems is are called gradient systems, and they have formed that there is a potential, and then there is derivative. So this is potential. And gradient system here is a derivative, and this is scalar function in one dimension. This is a one-dimensional derivative. In 2 dimensions is derivative. In 2 directions, 3 directions. So the gradient produces a vector quantity out of this. And if the first derivative of the system can be written in this form with a minus sign here, then your orbit will be descending. If you try to find a periodic solution, by the time you get back, you'll be away from where you started, and this will keep pushing you in the same direction. So you cannot have a periodic orbit. Now, I told you about conservative systems. How is that possible? Well, what happened in conservative system, it's the first derivative of momentum. So not x, but p, or the other variable, the velocity variable, in other words, acceleration, that's described by a gradient. And those systems allow for periodic solutions. But systems in which only have first derivative and everybody's pointing the same way, you cannot have periodic orbit. Then there are things that are called Lyapunov functions. Lyapunov was a Russian nobleman with a bunch of serfs, many serfs, making him rich and fat, but he was not a lazy Lyapunov, a lazy nobleman as those in War and Peace. He was an ambitious man, so he spoke, of course, French, as all noblemen would do, Russian noblemen would do at that period. And he was, in constant contact with Poincaré, the French school of mathematics. And his interest was proving that solar system is stable. The solar system that we have today will be there forever. Today we know it's not true, but we went through centuries of back and forth whether this is true. And one way he wanted to do this is he wanted to define some functions you could define on a state space or phase space of a system, such that you could show that in a surface or hypersurface in a state space, you can only fall in, but you cannot fall out. So all velocity fields on those hypersurfaces are pointing inward. That's the idea of the Lyapunov function. And that means that whatever happens in the system has to be confined in the volume defined by such surface. And to define a surface, one way to define the surface is writing some kind of function which on the surface is 0. That's called Lyapunov function. And then you use compute the velocity field any place, and if you can show it's pointing in, you have shown that this system is confined. Now, I don't want to do more on Lyapunov functions. Please, read the example in Strogatz. The reason is that they're almost impossible to find. There are a few examples, and nobody knows how to find them in situations where you need them. So, I'm not emphasizing it. It's a deep idea, a good idea, but hard to implement. Now, simple examples in few dimensions are easy to construct, but the real problems are in very, very many dimensions. And what this says, if I'm in 100 dimensions, I have to find 99 dimensional hypersurface which is some curved 99-dimensional manifold, which has a property that every place I look in this 99 dimensions, it might be compact, but it's big, the velocity points inwards. Good luck to you. It's the same kind of idea done in a more implementable way. And then there is one thing that actually everybody should know. At the end of 19th century, not only French were very good in mathematics, but the Swedish nobility was very good. They had a good mathematics school. So we have a theorem called Poincaré-Benedictson theorem. Not a negative thing, no periodic orbits, but this is making our intuition about having no choice but fall in or fall out from invariant surface in 2 dimensions, making it mathematics. And the idea of Poincaré-Benedictson theory is pretty simple. You play with your systems, you go to polar coordinates, you run it computer, and you get some feeling for it. And in the plane, you decide to define 2 curves such that if there were any fixed points in this problem, they're kind of inside one of those curves. And outside of the other curve in the plane. And you have an area in the plane which is free of fixed points. Then you check the velocities on these 2 curves. And this is same idea like Lyapunov, but it's doable in a plane. That's an example where. And if you can show that every point has velocity going in on the outer curve, so they're totally free, you design them. On the outer curve, everybody falls in, but on the inner curve, everybody also falls in. So this thing mathematicians like to call an annulus. Which has a property, and this will generalize to higher ideas if you can do it. If you can produce some kind of sausage in higher dimension and verify that everybody falls into this sausage. In the plane, it has to be 2 curves. Then what is this thing going to do? Can't do much. So what it will do, you'll end up on a limit cycle. So any point inside of this annulus cannot escape. It has to do something forever. And the only thing that can eventually do, it can end up on something that's a fixed point in Poincaré's section or a limit cycle. He has a nice example where you take the thing that we already did, that goes. But you couple it to the angle. And the only way you can couple periodic functions is by periodic functions, and those are sines and cosines. So the simplest way to do this is The stick something that cares about, like in pendulum, how far you're out, so you're dimensionally correct, times some parameter, mu. And if mu is 0, we already know what this thing does. So, and you still choose a version of that system in which you can make angle moving at constant velocity, but the radius gets deformed. So you will not be on a circle, but you'll be on some curve which is periodic but off a circle. And analysis is perfectly fine, but it shows you that it does that. In that case, only thing you have to exclude, there is only unstable fixed point at the origins. So annulus just has to be, it can be very, very small as long as you excluded the fixed point from it. And that gives you a nice example. Now, the other nice example that I really like and we'll spend time on, so we'll do it next time, glycosis. So what this book does, it just teaches you ordinary differential equation, nonlinear ones, but it gives them fancy names. So we're in a plane, there are two velocities. I start like for harmonic oscillator. Well, this would be a y for harmonic oscillator, but there is a parameter, a. So, I should be falling in because this is negative, so velocity is decreased, but I'm coupled to the other degree of freedom. And then for, perverse systems, which I cannot explain, but for example, Flavio Fenton uses such equations a lot in his cardiac dynamics research. There's a nonlinear term. And then there is another parameter here, B. So it says constant velocity, except I'm being affected by this term here. What does this thing do? Check in next week.